So let's start with some questions. Does anyone have any questions from any of the previous classes or say the tutorial?
I have one.
Yeah.
Just from last class, the rotation part.
Yeah.
Uh, So the inertia, moment of inertia were I, and zero. So why
Yeah.
was there zero? What's with the zero part?
Oh, yeah. So what we are doing is that we are saying that you know, so if you have like a very thin rod, so it's very thin, right?
Mm-hmm.
It's so thin that you approximate this rod by a line. Okay.
Mm-hmm.
Then so if you have three axes, that's one axis. Another is this axis, and another is this axis, right? So the moment of inertia around this axis is going to
Oh,
be
I
zero.
see. Yeah.
Yeah,
Okay.
yeah, yeah. That's all.
I forgot. Okay. Thank you, sir.
Yeah, no worries there. Yeah. Any other question?
I have a question about the last tutorial. There was that question, that was the one that Shujish was talking about with the moments of inertia. Um,
Yeah.
I think Nahi also said this, but I feel like the problem was not very well defined. Like I don't understand where the angles are coming from, or how I'm supposed to derive the Lagrangian.
Right. Okay. Uh, so yeah, I can repeat that. So suppose these are my axes. So x, y, and z, or as we want to say, probably this is a better picture. Now, so if my so molecule is like this, so this is one part. The other part is say, and so what I mean is that the dotted part is the part which is not in this quadrant. Well, not quadrant, but you know what I mean. 1/8th. Uh, so there is some stuff here, and okay. So this thing has like so this is the z-axis. So it makes an angle theta with the z-axis. Sorry about that, but you know what I mean, right? So now suppose that it's only rotating in a direction that around an axis that changes theta, right? So for example, it's I mean, we know that for us to be able to specify a direction in space, we need two numbers, right? Because a vector is given by three numbers, but a direction vector is given by two numbers. Okay, so let's say phi is fixed. Phi is fixed, but this this molecule is spinning in such a way theta is changing. If that is the case, then the kinetic energy of this molecule will be half I theta dot squared, right? Now, if it's actually spinning in such a way that phi is also changing, so let's assume the case where theta is fixed. Okay, if theta is fixed, then if phi is changing, what is going to be? It's kinetic energy, right? Well, you have to take into account the orientation of the axes, around which the rotation, the change of phi is happening, right? So if you look at the geometry a little bit carefully, you will see that it's going to. So first of all, because of the fact that its moment of inertia is the same around both of these axes, perpendicular axes, it's going to be this thing. But because of the orientation, you have to have
a sine squared theta term.
Yeah, a sine squared theta, and then yeah, and then phi dot is the is the direction of is the angular velocity, right? So both of these are kinetic terms. Okay, there is the potential energy in this case. And the reason why we write it as a Lagrangian rather than a Hamiltonian is because it makes the definition of what P theta and P phi are more clear, right? Because P of I is delta L by delta Q I dot. Okay? Now, it's a lot clearer if you take the extreme limit, right? The extreme limit would be, suppose that this molecule was oriented along the z-axis, right? In that case, theta would be 0, right? If theta is 0, then the axis of rotation for which phi dot is the angular speed, speed will be in the hang on. Sorry, not 0. If this was essentially if theta was equal to 90, right? If theta was 90, then this sine squared of theta would be 1, and then the molecule would be in the xy plane. And in that case, the axis of rotation would be along the z-axis for this angle, and then this would be just half I omega dot squared. Okay. So, the direction of the axis of rotation, because the way that we are measuring the angle with respect to the z-axis, the initial angle. And because we are measuring the initial angle from respect to the z-axis, the orientation of the second axis will have this factor of sine squared. Okay, Saif?
Yeah, I got most of it. I'm not still exactly sure why
I think
there
the
are.
geometry you have to figure it out yourself. I think
Yeah.
different
I'll do that.
different people are able to convince themselves differently of the geometry, but it's not a very complicated geometry. I like to think in extreme terms, like, okay, I wrote down a formula. Does this work for the extreme cases? Then by extrapolation, it should work in the intermediate cases. Right. I mean, for example, if the molecule was oriented along the z-axis, there would not be any kinetic energy associated with this, right? Which is exact, because in that case, theta is 0.
So basically, we're figuring this out kind of by inspection.
Yeah, exactly. I mean,
that was what I was confused about.
It's a geometry problem.
Writing the velocities in terms of cylindrical coordinates also helps, I guess.
Spherical.
Sorry, spherical. Yeah. Sorry.
Yeah. Okay. Any more questions? Okay, so if not, let's move on to our possibly last problem from the classical gas part. In the next class, before I start the quantum mechanics, quantum gases, I will probably do a review lecture on quantum mechanics and review/introduction. Because many of you haven't taken quantum mechanics. So, and also, even if you have taken quantum mechanics, there are certain concepts which are usually not taught in quantum mechanics, traditional quantum mechanics courses, which are useful in statistical mechanics. Concepts such as density matrices.